All right, section 3.1, part 2, sketching derivatives. So we've already talked about finding the derivative function, which is the derivative that, which is the function that outputs slopes of tangent lines at any point that you want. So you plug in an x value, and then the output is the slope of the tangent line there. All right, now what I want to be able to do, or what you to be able to do, is to take a graph of a function and then sketch what the derivative will look like from the graph of the function, okay? So in other words, you don't know what the function is, but you want to graph what its derivative is. So let's start off here with a function. Okay, so let's go. This function is going to be mostly positive, so we'll go 1, 2, 3, 4, 5, and then we'll go out, I don't know. Okay, like this. And so we'll start this function at 0, 1. It's going to go up to about 3, 4, so over 3 and up 4. 1, 2, 3, 4. And then we're going to have a minimum at 5, 1. So 3, 4, 5, 1. This. And then the graph is going to do something like this. All right, so as we're thinking about sketching the derivative of this function, let's think about the slopes. Okay, so I don't need to be super picky about the derivative. We will need negative values though. Okay, so here's x, and then on the y-axis we're going to put f prime of x, and the y-axis here is f of x. Okay, sorry, that took a minute to draw. All right, so now we are going to sketch. What I like to start with for the derivative is points that I know for sure. So I know for sure that the slope of the tangent line here at 3, since that's a maximum, the slope of the tangent line is going to be 0. So on the graph of the derivative, I'm going to go over to 3, and I'm going to put an x-intercept right there. All right. The other thing I know is that the slope of the tangent line at 5 also has to be 0. So I'm going to go over here to 5 and put an x-intercept on the graph of the derivative. What I know to the left of this maximum is that the function is increasing. Okay, in other words, if you were to sketch in a tangent line anywhere from here where it starts to the maximum, the slope of that tangent line would be positive. All right, and it's as you, what's a good way to represent this? As you get closer and closer to the maximum, those tangent lines are going to flatten out. They're going so the slopes of them will be less and less positive the closer and closer you get to the maximum. So in other words, somewhere up here, this graph is going to start. I don't know exactly what the slope is at 0, 1 there. So like I don't know what the slope of the tangent line is there, but it's positive something. I'm not going to be super picky about that, okay? But you know that it has to get closer and closer to the x-axis because the tangent lines are getting less and less positive the closer you get to the maximum, right? To the point where here it goes below the x-axis because now the tangent lines start decreasing because right here all the slopes are negative, okay, until you get to the minimum. So the derivative has to go below the x-axis. How far below? I don't know for sure. I don't really care that much actually. It's not going to be, it doesn't get super steep, but it doesn't get, it's not just like flat either. Again, I'm not super picky about how far below the x-axis you go here, just that you know that we've got positive slopes here, negative slopes here, in other words, below the x-axis, and then positive back over here, because in this section of the original function, I can't spell INC. In this section of the original function, it's increasing, okay? So the derivative must be positive over here, okay? And then it's positive for the rest of the domain to the right there, all right? So that's a sketch of the derivative. Again, start with your, where you know the slope is 0, and then figure out where it's increasing and decreasing, and then map that accordingly onto the derivative. All right, let's do one more. So we'll call that number 1. This will be number 2. All right, and if I'm really on my game, I will speed the drawing of this graph up here, so it doesn't take that long. Okay, so we have some points here. So we have -1. So that line segment, then we have 1, 1, the line segment there, and then we have a point at 4, -2, and a point at 5, 1. All right, so there is the original function. So we've got x axis f of x. And then let's graph the derivative here. So we have f prime of x and x. Okay, and so let's start at -1. So from -1 to 0, we know what the slope of all the tangent lines are from -1 to 0. The slope of all the tangent lines on that interval are the same. They're all -4, down 4 and over 1. So on the graph of the derivative from -1 to 0, we are going to graph -4. And it's going to have a closed dot here and an open dot here. It has a closed dot here because we're going to take a one-sided derivative, a one-sided limit to get the slope on that one. And then at 0, the graph breaks here. Okay, so we have a corner. It's what we say is not differentiable here. Or if you zoomed in repeatedly, you would find that you could not linearize that the graph there. It would not ever become a line. The further you zoomed in, you still get a corner. All right, so anyway, so right here, the slope changes to +1. So at 0, or from 0 to 1, we have a slope of +1. Okay, so it looks like that. And then from 1 over to 4, we have a slope of, let's see, down 1, 2, 3, so -3, and over 1, or right, 1, 2, 3. So a slope of -1 there. So we have, again, an open dot because we can't differentiate at the corner, over to 4. So 2, 3, 4, open dot there. The graph looks like the slope is constant on that interval. And then from here to here, so that's what, from 4 to, I think I went over too many, it doesn't matter. From 4 to 6 is up 1, 2, 3, and over 2. So that'd be 1.5, so slope of 1.5 from here to here. And again, because it's an endpoint, we take a one-sided derivative, a one-sided limit, and we can evaluate it there with a closed dot. But at these values, there is no derivative. Okay, so that's how you sketch the derivative from a graph that is a series of line segments. So when you have lines, you can just find the slopes and compute them. When you have a curve, you're doing much more approximating. All right, now I'll say it one more time. I'm not super picky about the exact values here. All right, except for the x-intercepts. You should be able to get the intercepts. All right, I think that's kind of it. So sketching from a smooth curve, sketching from a series of lines, that's how you sketch the derivative from the original function.